In this lecture, I'm going to cover some ideas from 4.4 in the text, which is called Shape of a Graph. I think of this more as the ideas related to the second derivative and how that is related to the shape of the graph, but then also the second derivative test for critical points to determine if a critical point is a maximum, minimum, or possibly neither. So I guess I just want to emphasize that I feel like with as much work that we do with graphing calculators and computers, I think the ability to use information about the derivative or second derivative of a function in order to sketch graphs might not be so relevant. We have lots of technologies that can do that, but I think that the ideas embedded here in terms of the relationship between a function and its derivative and its second derivative, and what that means for points of maximum or minimum, and especially we'll see this when we get into 4.6 and talk about optimization problems, trying to, in situations that we could use calculus to try to find the maximum or minimum of a function. That's where I think these are of more practical value. So I want to connect back to the work that we did in Lab 9. So I had you investigate a graph and look for what would the shape of the graph be when the first derivative is increasing. All right. So what you should have gotten was something like this. All right. So you can see here, although it's negative along here, and this was the part that might have been hard for some of you, it could be negative and still increasing. When I say increasing, it means that we're moving from left to right here. You know, for example, along the x-axis. X values are getting bigger, and as we do that, our tangent line, the slopes of the tangent line are becoming less negative. Therefore, they're increasing, right? Till we get to the point of 0, and then they're positive, and then they're getting bigger. So along here, this would be the first derivative is increasing. All right. So if the first derivative is increasing, that means that the second derivative is positive. And that goes back to the idea that if a function is increasing, then its derivative is positive. So there's the same relationship between the second derivative and the first derivative. Since the second derivative is the derivative of the first derivative, then if the first derivative is increasing, the second derivative is positive. So likewise, if the first derivative was decreasing, we had a shape like this, right? Again, as we go from left to right here, although the slopes of the tangent line here are positive, as we go from left to right, they're becoming less positive, right? They're getting closer and closer to 0. 0, obviously is a horizontal tangent line. And then coming on this side, they become negative, and they become more and more negative. So in this case, f prime is decreasing, and the second derivative is negative. Again, for the same reason, a function is decreasing. In this case, the first derivative is our function. The function is decreasing, then its derivative is negative. So we call this shape here, we call this concave up and concave down. So although I wanted you to use this idea of the first derivative increasing or decreasing in order to get these, this is what you want to tie together here, right? That when your second derivative is positive, the shape of the graph along that point, or along that, well, let me go ahead and just define it. So we say, suppose the second derivative, let's say it exists for all x values in some open interval on a to b. All right. So if the second derivative is positive for all x, that little symbol just means that x is in this interval. It's somewhere in between a and b. For all x and a in the interval, then f is concave up. Notice that we're using the second derivative to say something about the function. All right. When I'm graphing this here, this shape, this is the shape of f. All right. The f prime, those are the slopes of our tangent line. In this case, they're increasing. In this case, they're decreasing. And then f double prime just tells us that the shape of f is concave up here and concave down here. So likewise, if the second derivative is negative for all x in a b, then f is concave down. All right? So the other thing I would like to define here is an inflection point. An inflection point is a point where the concavity changes. All right, we go from concave up to concave down, or from concave down to concave up. So graphically, let me just give you a couple of examples graphically. So let's say we could have something that kind of goes, I don't know, let's see. We have something like this. All right, so if we had a curve like this, clearly it's concave up along here, and it's concave down along here. So somewhere in between, you can kind of think of separating these into two, right? Like I could have a piece that looks like this, and then I could have another piece that looks like this, right? With these two pieces, they kind of, if we pull them apart, this right here, that point where the concavity changes is an inflection point. Okay? So you just have to kind of, when you first begin looking at graphs, it might be a little bit mysterious. It's a gradual thing, right? You know, somewhere in here we go from concave up to concave down. But if you think about maybe kind of pulling them apart, another way to think about it is if I have like my fingers here, concave down, and I have another piece that's, let me get this on the video, concave up, kind of when I put them together, that's my inflection point. All right? Okay. So what does this mean? Well, it also means that the sign of the second derivative changes, right? Because here I have that concave up, I have that the second derivative is positive. Over here where it's concave down, I have the second derivative is negative. All right? So if we're going to go, if the second derivative is going to go from positive to negative, what do we know about what's going to happen in an inflection point? Well, we're going to have at the, we say f prime of c is 0, all right, then that could be an inflection point. All right. If it's an inflection point, I'll just abbreviate that IP, and then that implies that the second derivative is 0. But we can't necessarily see anything about going this direction. All right. So let me give you an example of how we might do this. I'm not giving you a graphical example. Let's just look at an example of a function algebraically. Let's say we have x to the 5th minus 5x to the 4th. All right. So let's try to find kind of the intervals of concavity, like where this thing is concave up and concave down, and find the inflection points. All right. So to get the second derivative, well, first I have to take the first derivative, right? So that's 5x to the 4th minus 20x cubed. But I'm after the second derivative, so let's do it again. Polynomials are easy. 20x to the 4th minus 60x squared. All right? So in order to find, we're going to use this idea here that we know that if we have an inflection point, that the second derivative is 0. So if we set this equal to 0, we will find at least our candidates. Remember, second derivative being 0 doesn't necessarily mean we have an inflection point, and actually this example is going to show that precisely. But we need to kind of have an idea where to look for them. So we set it equal to 0. I can factor out what? 20x squared here. right? And I end up with just x minus 3 left here, right? Equals 0. So 20, sorry. So either 20, so the product of two things is 0, so either 20x squared equals 0 or x minus 3 equals 0. Well, the only thing that would make this true is for x to equal 0, and of course here I would have x equals 3. All right, so I can make a little sign diagram for the second derivative. All right, we have 0, and then we have 3. Okay, so I know that the second derivative is 0 here and 0 here. I want to know what the sign of the second derivative is in between here. So we could maybe just use this version, this factored version of the second derivative to test some points. So very similar to testing critical points, we know that concavity can only change when the second derivative becomes 0. So any value I pick out here will have the same sign for the second derivative. So let's try, for example, f prime of negative 1. All right. Well, that's going to make this, the 20x squared. Again, I'm only worried about the sign here, but when I square negative 1, it becomes positive times 20. That's positive. And negative 1 minus 3, that's going to be negative, and so that product is negative. So it's concave down in there. Let's pick something in between here. For example, f prime of 1. So again, putting in 1 here, we square it, multiply by 20, we get a positive. Putting in 1 here and subtracting from 3, that's negative, and the product is negative, so it's negative in here. And then finally, let's pick something out here like 4. All right, square 4, multiply by 20, that's positive. We don't really care what exact number it is. And in here, 4 minus 3 is also positive, so that's positive, and we're positive out here. So we are concave down here, concave down here, concave up here. So here we have an inflection point because the concavity changes. The sign of the second derivative changes. That is how an inflection point is defined. It's not defined by when the second derivative is 0. It's defined by when the concavity or the sign of the second derivative changes. This here is not. 0 is not an inflection point because the concavity did not change. All right, so we'll talk about this kind of a scenario more when we talk about the second derivative test in the next lecture.